Hey there, welcome to Pomodoro Joe for Monday, October 30th, 2023. Today we're looking at LeetCode problem 1356. Sort integers by the number of 1 bits. This is an easy problem. All right. You are given an integer array. Sort the integers in the array in ascending order by the number of ones in their binary representation. And in case of 2 or more integers have the same number of ones, you have to sort them in ascending order. All right. Return the array after sorting it. Cool. So this should be a fun one. Now we have an example, 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and the output is 0, 1, 2, 4, 8, 3, 5, 6, and 7. That's because 0, 1, 2, 4, and 8 all, well, let's see, 0 has 0 ones, 1, 2, 4, and 8 all have 1 bit, 3, 5, 6, and 7, let's see, 3 and 5 I believe have 2, 6 is 2 as well, and 7 is 3. Okay. All right, so this seems pretty straightforward. We'll put 25 minutes on the Pomodoro timer here, and we'll get started. So for this, I think we're going to rely on some of the built-in Python functions. Now, most high-level languages will have similar functions that you can use. So even though we're using like Python-specific sorting, you'll find sorting in C, Swift, C++, Java, JavaScript. Most other languages will also have these types of sorting algorithms or functions for you. All right, so for this, we'll have some result. Let's see, we'll make this an empty array to start, and then we'll return the result at the end. In fact, I might just go ahead and do the assignment here. So let's use our result, and it's going to be a sorted version of our array. So sorted array. Now this sorted function will take an input array and it will create a new array of the sorted array and assign that to our result here. So we're actually going to get an entirely new array out of this. Now you could also call sort. Now array.sort will do the same thing, but it will sort the array in place, meaning it will replace the existing array with a new sorted version of that array. All right, so we're going to sort our array. Now this sort by default will sort in ascending order. So it will just sort all of our elements in the array in increasing size. Now I don't want to do that. I want to sort it by some specific sort criteria, this number of 1 bits in their binary representation. So to do that, we actually pass in another variable here, or another argument. It's called the key. In Python, they call it the key. In other languages, they might call it the comparator. There are different names for this, but in Python, it's called a key. And so I'm going to assign the key to a function. And in this case, I'm going to make a lambda function. So that is a function that doesn't actually have a name here. So lambda, and it's going to take one variable x. So basically, this is going to go through every element in our array, and it's going to call this function, this lambda function, passing in that element. So that element is going to be this x here. So it's going to pass that element in as the argument to this function. And now I need to return a tuple. And in this case, the tuple has to be essentially the first element in the tuple will be the first thing it sorts by. The second element in the tuple will be the second thing it sorts by, so on and so forth. So you can have as many things as you need. So in our case, we need to sort by the number of 1 bits, and we need to sort by, in case there's a tie, we need to sort by the actual number itself. So let's have a function here. So number of 1 bits. And we'll pass in x. And then our second value in our tuple will just be x itself. All right, so this is a little bit confusing, but let's break it down. So our result will be the sorted array, passing in the array, and we're going to sort by this key. And that's going to be a function. It's just an unnamed function, so it's in place here called lambda. And that's just a function that takes x as a parameter. And this x will be filled in by this sorted with the element itself. So this is just going to take the first element. So it's going to be like 0, and it's going to pass 0 into this function here. So it's going to be number of 1 bits 0 or 0 itself. And then it'll pass in 1, so it'll be number of 1 bits passing in 1, and then number of 1 bits passing in 2, so on and so forth, for every element in our array. Now I don't have this function yet. I'll have to create this function. So the number of 1 bits, it'll take some variable x, or some argument x, and it will return the number of 1 bits, or 1's bits, in the binary representation of that number. And again, this is going to be a tuple. This lambda function returns a tuple where the first element is the number of 1 bits. And in case there's a tie and two elements have the same number of 1 bits, well, then it will look to the second element in our tuple to sort, and that's going to just be the element itself. So that's specified right here. All right, so now we have to actually create this number of 1 bits function. So let's do this. All right, so we'll define something here. Def, number of 1 bits. It takes just one argument, x, and we need to return the number of 1 bits in the binary representation of x. Now, I'm going to break this down into our own function, but there are shorter ways to do this using some Python built-in methods, but let's actually go through the process of building our own function that does this. So for this, we'll have some count, and we'll start it at 0, and we'll return the count at the end. Okay, and now we'll have to go through every bit in our x. So for this, I'll say while we still have some x, so while it's not 0, let's see, we'll need to count this bit, so count will increase if this bit is a 1, or it stays the same if this bit is a 0. So we need something here that will give us a 1 if this bit is a 1, or a 0 if this bit is a 0. Well, to do that, we can take our x value, and we'll do a bitwise AND with 1. So this is just saying, look at the bits in x, and do a bitwise AND, so that's our bitwise truth table. So 0 and 0 is a 0, 0 and 1 is a 0, 1 and 0 is a 0, 1 and 1 is a 1. So this is going to look at x, compare all the bits to all the bits in this 1. Now this 1 will just be bitwise 0, 0, 0, 0, 0, 32 zeros and a 1 at the end. So, or 64, however many bits you need to represent a number. It'll be that many zeros and a 1 at the very end. So we're really just comparing the least significant bit in x to 1, and if it's 0, this will return a 0. If it's a 1, it'll return a 1, and our count will increase. And then we need to shift our x. We need to, let's see, now that we've looked at this least significant bit, we need to shift our entire x to the right by 1 so that we can drop that bit and we have a new least significant bit. So then x becomes x shifted right by 1. All right, so we're going to keep checking our least significant bit, shift our x. We're going to keep shifting our x until eventually we run out of bits and x is just 0. Okay, so that should be it. We'll have this function, some number of bits. It's going to count the number of bits by comparing the least significant bit or masking all the other bits and just looking at the least significant bit in x. Then we shift to the right until we run out of bits and x becomes 0. All right, and then we have our sorted here. We're going to sort our array by this lambda function. It's going to take 2 arguments, or it's going to take, sorry, 1 argument, the element itself, but it's going to return a tuple with 2 elements. 1, which is the number of bits, and 2, the element itself in case there's a tie. And then we return the result at the end. All right, let's see if this works. Okay, it seems to work. Let's submit this, see if we can pass all the tests. And we pass. All right, let's see. It's not a great solution, 41% for runtime, 40-something% for memory, so not great. Now we can come back here and do a little bit of cleanup. So one thing, this result we don't really need. We can just directly return this sorted here. That's one quick little thing we can do. What else could we do? We could inline some of these. I kind of like it this way. Let's just see if this saves us anything. No, it actually makes it worse. It saves us some memory, but it makes us worse in runtime. That's interesting. All right, we'll jump back here. A couple other things we could do to speed this up. One thing we could do, instead of sorting this array and returning a new version, we can actually call sort. So I believe, let's see, this will be array.sort. Oh, of course, because this is doing the return on the function basically. So I need to actually call array.sort first, and then we can return the array. Okay, that works. Now this should save us some runtime and memory. Now it's debatable whether or not you should even do this. Actually, it doesn't save us anything. So basically the same that we had before. So I would say don't do this. The reason why it's debatable is this is actually changing the input Now, if you're using this in a production environment and somebody's passing data around and you modify the data unexpectedly, that could cause problems with the rest of your code. So I would not recommend doing this. Let's go back to sorted here. Okay, now another thing we could do, this function, we're doing our own comparison, counting the number of bits. This is great to learn, this is great to know, but there are better ways of doing this. Now, Python has some built-in functions that let you basically do this a lot faster. So we could do the binary representation of x, and then we can count the number of ones. All right, let's see if this works. Oh, we have to return this. Okay, still works. Let's see if this gives us any improvement. And it's a significant improvement. Let's see, now we went from a 20-something% to a 78% for runtime. We lose a little bit in our memory, we go down, so it's a trade-off. Now, we are doing more function calls here because we're doing this binary call. This will convert x into a binary representation of x, and then we're going to call count to count the number of ones in the binary representation of x. Okay, one last thing that I'll do, and again, not necessarily recommending this, but just to gain a little bit of speed here. So we have this function, this num of 1 bits function. Now previously we had a bunch of code in here to basically mask and shift bits. Now that this is just a one-line function, we can replace the internals here with this one line. So we can grab this, just replace this here, and then we don't need this. That cuts this down to a one-line solution. See if it works. All right, and that works. It actually goes down a little bit in our runtime. We were at a 78% and now we're down to a 53%. So it actually doesn't save us anything, which is a little surprising, but it does make the code super compact. So it's kind of a trade-off. Personally, I prefer the previous one. It's called intent-based programming. So essentially you have functions that sort of describe the intent. The intent here is to count the number of ones bits. This might even be better if it was called count number of 1 bits, but I just need something that will count the number of 1 bits in this place here. Now, I don't really care how it's done. Well, I kind of do, but I don't have to care how it's done because I just have the intent here. The intent is to get the number of 1 bits in this number x. Now, I can replace the internals of this with anything I want at this point. So I can replace this like bin x count numbers, 1 with anything else. So this gives me a chance to actually go through and optimize this function without having to change the external dependency. Okay, well that's it for me. I hope you enjoyed this. I hope you had fun. I hope you learned something. I hope you can go out and write better code.